All right, good. Welcome back. Now what we're going to do is we're going to show how we can use our restatement of Bayes' theorem in terms of hypothesis and evidence as a way of solving the problems that I asked you to try on exercise set 7.5 from the PDF from Mary Lee Salmon's book. But let me first say one thing about this. Many of you asked the question, how do I determine what is P and what is Q? Now you have a clear answer. When you get these problems, what you're going to do is you're going to ask, what is being proposed as the hypothesis here, and what is being proposed as the evidence, and that will give you a straightforward answer, because once again, all we've done here is just substitute the H for hypothesis for P, and the E for evidence for Q. So Marisha, if you will read problem number 1 on the exercise set 7.5.
Approximately 1 out of every 20 American women develops breast cancer by age 50. Early detection is important to prevent fatalities. Suppose that doctors develop a screening test that is inexpensive and non-invasive. It does not involve x-rays or any surgical technique. While the test apparently does not give false negative readings, studies indicate that it produces a false positive reading 20% of the time. When a test is positive, the patient is advised to undergo further testing with x-rays. Mrs. Griffin, age 50, has no symptoms, but she has made an appointment for the screening.
Okay, excellent. Let's stop there. So what we have there are the basis of the data, and you will recognize that this problem is very similar to a problem I gave you when we first started talking about probability and to test your intuitions about probability. Okay, now, what is question number A?
Okay, A. What is the prior probability that Mrs. Griffin has breast cancer?
Okay, let's stop here because now notice that we have been given an indication of what the hypothesis is. The hypothesis is that Mrs. Griffith has breast cancer. And the prior probability before the evidence of this new test is taken into consideration was given in the statement of the problem. It is 1 in 20 because Mrs. Griffith falls into the category of American women for which 1 in 20 have breast cancer. So that particular prior probability is 0.05. Stop.
Suppose Mrs. Griffin has the screening test and the result is positive. What is the posterior probability that she has breast cancer?
Okay, now notice we're now asking for the possibility that Mrs. G has breast cancer given that Mrs. G got a positive test on our test. So now we have our hypothesis and we have a new piece of evidence and we want to re-examine the probability of the hypothesis in light of this new piece of evidence. Now it's just a matter of figuring out all these values for Bayes' theorem and plugging them in. We already know what the prior probability of the hypothesis was. That was 0.05. 1 in 20 American women that are in Mrs. G's category have breast cancer. Okay, now we need to know what is the probability of the evidence. What is the probability that Mrs. Wilson got a positive test given that, or assuming that, she has breast cancer? And we were told that there are no false positives. So the probability that she got a positive test, given that she has breast cancer, is a probability of 1. Okay? Now, the next one, we have our same value here. Now we have to get the rest of the values. What is the prior probability that Mrs. Griffiths does not have breast cancer? That's 0.95. Those are that because of the demographic that she's in. Now, what is the probability that Mrs. Wilson got a positive value on this test, the evidence, given that she does not have breast cancer? And we were told that there's a 20%, false negative rate, and so we plug that value in here, and now we've got our entire situation set up as an application of Bayes' theorem. We can now simply do the mathematics. 0.05 over 0.05 plus 0.95 times that. That's 0.19. And when we do our math, this equals 0.05 over 0.24, or as you can tell from this, just a little bit, you can do the math and you see this here, it's going to be just a little bit better than 1 in 5.